So if you've ever dipped your toes into quantum computing, you've probably learned that quantum states are just simple vectors. But what if I told you that's kind of like learning the alphabet but not the whole language? Today we're going to explore the real, more powerful language of quantum mechanics. So let's start with that idea. Quantum states are just these perfect, clean little vectors. But in a perfect world, on a perfect computer, that is. But in our world, it's not perfect. And reality is much more complex. And for that, we need a mathematical language that can actually keep up. And here it is side by side. On the left, you've got a familiar picture. States are vectors, simple and clean. But on the right, that's the general formulation. That's the upgrade. Here, quantum states are represented by these special things called density matrices. This is the leap we're about to unpack. So you might be asking, why bother? Why do we need to bring matrices into this? I mean, what's really wrong with the simpler vector model? Well, let's take a look at where it starts to fall apart. Look, state vectors are fantastic for describing a single perfectly known quantum state, but what happens when you have a mix of states, like for example some randomness, or what happens when noise from the environment messes with your qubit? What if you have two entangled qubits, but you only care about what's happening to one of them? The simple vector notation doesn't have a good answer for any of these very real situations. So to build our more powerful description, we first need to get the hang of the notation that makes it all possible, bracket notation. And trust me, it's not as scary as it looks. It's actually an incredibly clever shorthand. First up is ket. And honestly, if you've ever seen quantum states written down, you've already seen a ket. It's just a fancy name for what we already know, a column vector that represents a quantum state. That angle bracket pointing out to the right, that's your signal that you're looking at a ket. And of course, if there's a ket, there has to be a bra. See how the bra-ket is pointing the other way? This is the row vector version. To get from a ket to its matching bra, you just flip it on its side. That's the transpose. And to take the complex conjugate of everything inside, that's the ket's natural partner. Now here's where it gets interesting. When you put them together like this, bra first, then ket, you get a bra-ket. This is the inner product. You're multiplying a row vector by a column vector, and that crunches down to a single number. You can think of it as a way to compare two states to see how they overlap. And this is the real magic trick. If you flip the order, ket first then bra, you get a ket bra. And this doesn't just give you a single number, no way. This is the outer product. You're multiplying a column vector by a row vector, and it blows up to a whole matrix. This is the matrix building tool we need to make that jump to a more general description. So with our bracket language ready to go, we can finally meet the star of the show, the density matrix. This is the mathematical object that's going to solve all of those problems we talked about a minute ago. So what exactly is a density matrix? It's often written with the Greek letter rho, and it's any matrix that follows two key rules. First, it has to be positive semi-definite. Now that sounds complicated, but the intuition is pretty simple. It means that all of its eigenvalues, the numbers that describe how it stretches things, are either positive or zero, no negative stretching allowed. And second, its trace has to equal 1. The trace is even easier. You just add up all the numbers on the main diagonal, so non-negative eigenvalues and a trace of 1. If a matrix checks those two boxes, it can represent a valid quantum state. This is how we connect the old world to the new one. How do you take a perfect pure state vector, our old friend, and write it in this new language? You just take its outer product with itself. You use that ket-bra operation we just learned. The density matrix for a pure state is simply that. It's that easy. This diagram is just fantastic. It really shows the whole idea. Imagine this gray oval is the entire universe of all possible density matrices. Every valid quantum state lives in here. Now look at the states right on the edge, on the boundary. Those are pure states. Those are the special cases that we could describe with simple vectors. But what about all that space inside the oval? All that interior? That represents the mixed states. These states are with noise, with uncertainty, and vectors alone can't go there. So how do we describe those points on the inside? Well, a mixed state is exactly what it sounds like. It's a probabilistic mix of other states. If you got a system that's in state 1 with some probability and in state 2 with another probability, the total state of your system is just this beautiful, simple, weighted average. This is how density matrices handle randomness and uncertainty so elegantly. So we have this new amazing tool. It's more general, it can handle uncertainty, and that's great. But what does this powerful framework actually unlock for us when we're trying to model the real world? This is a crucial takeaway. The density matrix framework is complete, and that's a really powerful word. It means that physically possible process that quantum states can go through, literally anything, can be described as a map that takes one density matrix as an input and gives you another one as an output. An ideal quantum gate, a noisy interaction, a measurement. It's all just a transformation of a density matrix. We call these transformations quantum channels, and because of that, we can lay out a completely general recipe for a quantum algorithm. You start with your initial state. You can bring in a helper system like a little workspace. You apply some big operation to the whole thing, then you perform a measurement to get useful info out. This whole assembly line can be described perfectly and rigorously using the density matrix formalism. So let's put it all together. By making this move from vectors to density matrices, we've done more than just add a new tool to our toolbox. We've actually adopted a much more profound, unified way of looking at information itself. I mean, just think about how flexible this one thing is. The single mathematical object, the density matrix, it can describe it all. It can be a pure state, which is just our old vector in disguise. It can be a mixed state, capturing noise and probability, and it can describe just one half of an entangled pair, which is incredibly useful. And what's really fascinating, it can represent purely classical information. That just turns out to be a simple diagonal density matrix. It's one single framework for quantum and classical information. And that leads us to the fantastic final thought we have here. The decision to represent quantum states as density matrices is not just some minor detail, it's the foundational choice. Once you make that one choice, almost everything else about the math of quantum information just follows logically. It's the master key that unlocks the complete and really beautiful language of the quantum world. Thank you all for listening. This is Quantlock.